Let's get started here. Brand new unit 2.1. We are going to start off talking about relations. And unlike human relations, which are overly complicated and unnecessarily filled with drama, mathematics relations are pretty standard and straightforward. I suppose the full title should be Relations and Functions. I think we went up to 1.7b. Yeah. So, like with everything, whenever we learn a new concept, knowing what the terms mean would be important. So let's start off with some vocabulary. In a nutshell, to simplify things as much as possible, the word relation in mathematics is simply a connection or a link between objects. Doesn't matter what that object is. If I linked the color green to the animal frog, I created a relation. If I linked the number 2000 to this car, that's relation. Obviously, in mathematics, we're only interested in relations that links numbers together. But technically, you can link whatever you want. Other words that I'll be using a lot in this section or in math in general is input and outputs. So the input, as the word suggests, is a value that you put into a relation. No duh. Output, you can probably guess its definition. A value that you get out from a relation. So inputs, as the name suggests, are numbers that you are literally putting into a relation, and outputs are numbers that you get from a relation. Now, if I were to collect all those numbers together, collect all the numbers that I'll be putting in, collect all the numbers that I get out, we create what is known as a domain and range. So the domain in math simply means the set of all inputs there's no standardized letter or standardized variable, but the most common variable that we typically use for the domain, the most commonly used variable used for inputs, is x. So you can sort of think of the domain as the set of all x values. And if you got an A star in kindergarten and you mastered your opposites, you can probably figure out the definition of range. It's the set of all outputs. No duh. And while it's not a universal law, we typically use y values. There are lots and lots of different ways to see relations in mathematics. So ways to represent relations. The standard classical way to represent relations is to use an ordered pair or use a coordinate. For example, I'm just making up numbers. 1, comma, negative 2. That's a relation. I'm linking the number 1 with the number negative 2. 5, comma, 7. That's a relation. Decimals, fractions, positive, negatives, doesn't matter. 1/2, comma, 0.7. That's a relation. Ordered pairs are coordinates that are floating in space. If you want to sort of organize them, you could represent a relation using a table. And all it is an ordered pair, but in an XY table format. So literally, it could be the same thing, but you're organizing it with the table. So 1, 5, 1/2, -2, 7.7. I typically would have wrote this in order, but I just decided to do it randomly. But these two guys say the same thing. You can see relations graphically as well. And in hindsight, I chose very, very crappy numbers because this is going to be hard to plot. But you can visualize relations using a regular X, Y graph. So 1, -2 would look something like this. 5, 7 would look something like that. 1/2 and 0.7 would look something like that. So you can write them as an ordered pair, you can put them as a table, or you can graph them. Another way you can visualize relations, which is not really used a lot in Algebra 1 and Algebra 2, I don't know why, but it's sometimes useful when you get into higher mathematics, is a mapping diagram. Especially if you take abstract algebra, which, if I can plug it in, is a very, very fun class to take in college. A mapping diagram sort of it visualizes the entire set of domains and ranges. So you typically represent the domain as an oval, domain as a range, and you just put your domains and range inside these ovals. So in my example, my domains consisted of 1/2, I'm going to write them in order, 1 and 5, and my range consisted of -2, 0.7, and 7. And you visualize these relations using connecting lines. So I'm going to, in our example, 1/2 was connected to 0.7, so I'll draw a line like that. 1 was connected to -2, and 5 was connected to a 7. So that is an example of representing this relation. Each format has its own, pros and cons. Graphs are great representations of relations because you can see the bigger picture. You can see patterns easily. The downside is, depending on your tick marks, depending on how neat the graph is, it's very hard to read what the specific numbers are. Ordered pairs, tables, and mapping diagrams, they're very easy to read what the relations are, but it's sort of hard to see the overall picture. But they do have some advantages. For example, if I ask you this question, and this might be a question on a quiz or a test, whatever. Question: what is the domain? With a graph, that might be hard to do because you're going to have to read these tiny tick marks. But with the ordered pairs, tables, and mapping diagrams in front of you, you guys should be able to answer this question. Recall the vocab word. Domain is the set of all of the inputs, all of the x values. Well, if you have the ordered pair, the table, the mapping diagram in front of you, what's the domain? Domain is the set of all x values. So what's the domain? 1, 5, and 1/2. You literally just read it, right? I like to write them in order, so I'll go ahead and write it as 1/2, 1, and 5. That is the domain. Easy peasy. Question: what is the range? And I hope if you have the ordered pair, table, or mapping diagram in front of you, it shouldn't take a lot of thinking. You know the range is going to be -2, 7, and 0.7. You literally just read it. To write things in order, -2, 0.7, and 7. Right? So these different representations of relations do have their uses. I personally like a graphical representation, but if I ever have to do domains range, having a table or the ordered pairs is sort of nice. I did say at the beginning that literally anything can be a relation as long as you link it together. I'm going to link green with frog. That's a relation. But we're interested in mathematics of one special type of relation, and we call that special type a function. Now, the definition of a function is it's going to be relations, a special type of relation. It's a relation for which every input has exactly one output. That is the mathematical definition of a relation. Or excuse me, a function of a function. I sort of like to think of function, this is a very cliche math thing to do, but I like to think of a function as a machine. Think of it as a vending machine. Right? Vending machine is a great analogy for an input-output function. You know, vending machine, you go up to it, you press a button, and you get stuff out, right? If I press the Cheetos button, what do I expect to get out? Cheetos. The very next day, press the Cheetos button, what do I expect to get out? Cheetos. So if that machine is working properly, if I press Cheetos, I should get Cheetos out. What if one day you press Cheetos and you get Cheetos out, the very next day you press Cheetos and you get Doritos out? Would we be saying this machine is working? No, because for the one input, pressing the Cheetos button, I got two different outputs, Cheetos and Doritos. So in that example, it would not be a working machine, it would not be a function. So that's all this definition says. A function is simply a machine, a relation, such that for every input you put in, you're only going to get one output. And there are a lot of ways to spot this visually. So I think an easy way to figure out this definition is to look at examples and non-examples. So some examples of functions. What if I gave it to you in ordered paired form? Say 1, 3, 2, 5, 8, 9. This technically is a function. Why? Well, what is the domain of my example here? 1, 2, and 8. This input of 1 has an output of 3. That's just one number, right? This input of 2 has an output of 5, which is just one number. This input of 8 has an output of 9, which is just one number. Every single input has one number output. This is a function. 1, 3, 1, 3, 2, 8. This technically is a function. Some people might say, wait a minute, Mr. Vo, you copied it. You got two ones here. That is true. That's just like me pressing the Cheetos button twice. Well, for every single time I press the button, what number did I get out? 3. And that is a machine that works. Hey, every single time I press the 1 button, I get the number 3 out. So although I duplicated, this still technically is a function. I could give it to you in a mapping diagram. If I had something like this, I'm lazy. 1, 2, 3, 4. Actually, that's not laziness. That's just not being creative. 5, 6, and 7. Let's connect 1 to the 7, 2 to the 5, 3 to the 5, 4 to the 6. This technically is a function, even though two arrows are pointing to the 5. Because remember, in a mapping diagram, the first oval is the domain, the second oval is the range. So we agree that the domain is 1, 2, 3, 4. How many outputs does this 1 have? 1. How many outputs does this 2 have? 1. How many outputs does this 3 have? 1 and 4. 1.
I'm just kidding.
It's sort of like cute and funny the first time, but when you deliberately give wrong answers, it's no longer funny. No, because when I asked, what do you get when you press the Cheetos? You said Doritos.
Oh.
Yeah, so this is your second time.
Okay.
So although this output of 5 has multiple arrows pointing to it, the definition of function focuses on the input. And if the input only has one output, technically it is a function. Let's look at some non-examples, or rather examples of non-function. So what if I give you a whole bunch of ordered pairs, say 1, 3, 2, 5, 1, 7, 3, 9. This would not be a function because here we have the same input having two separate outputs. So this violates the definition. I would say not a function. What about if I give you a mapping diagram? 1, 2, 3, 4, 5, 6, 7. Let's say I map 1 to 6, 2 to 5, and 2 to 7, 3 to 6, 4 to 5. This would not be a function because I can see the input of 2 has 2 arrows going out of it, which violates the definition. Question?
So is the whole thing not a function or just two?
Very good question. So does that mean just, the number 1 is not a function in the first example, or the number 2 is not a function in the second example? A function is the entire relation. So if one part is bad, the whole guy is not a function. So I would say the entire relation is not a function. So if I give you points, table values, mapping diagrams, it's very easy to see whether or not you have a function or not. But when I give you a graph, that can be tricky. Fortunately, there is a nice test to see whether or not a graph is a function. We call it the vertical line test. And the vertical line test states this. I'll put it in quotes. A relation is a function if and only if. So in math, if you do a lot of math writing, a lot of professors, a lot of mathematicians get lazy and use abbreviations. IFF in math is always if and only if. What if and only if means is you can read the sentence forwards and backwards. A relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. End quotes. What the heck does that mean? As always, I think seeing examples highlights things better. So I'll do an example of a function, an example of not a function. So suppose I had a discrete graph, something like this. This is technically, and just draw random points. This is technically a relation because we saw that we can represent relations graphically. Why is this a function? Well, you sort of have to imagine slicing this graph up vertically, right? You run it through a paper shredder, bless you. And what you want to do is you want to visualize vertical lines running through your entire relation. Since, it's hard to see what I'm thinking, I'll go ahead and draw it out on my paper. But imagine a vertical line going through this relation. How many points does that vertical line cross? Once. Draw a vertical line through this relation. Only crosses once. Draw a vertical line through this relation. Only has 1 point. As a matter of fact, no matter what vertical line you draw, you'll only carry or you'll only touch at most 1 point. That's what it means to be a function. No matter what vertical line you draw, you only contain one point of the relation. It works if your graph is spotted or scattered like this, or if you have a smooth graph, like, some squiggle graph. Let's say you have this squiggle graph here. Even in the squiggle graph, the idea is that no matter what vertical line you draw, you can draw vertical lines anywhere you want. It's only going to cross the graph at most one time. Oops. My bad. I killed the graph. Squiggle graph. There you go. Let's take a look at some non-examples. What does a scatter graph look like when it's not a function? Say you have a scatter graph going on. Right. You can easily tell a scatter graph is not a function when you have stacked points. So we can see here, for one vertical line, we have two intersections. So this is not a function. What if my graph was solid? A circle is a good example of non-functions. If I have a circle here, you can see that any vertical line I draw will cross more than once. So that is not a function. Are we okay with how to tell if a graph is a function or not? Very easy. Just slice it up and down a whole bunch of times. If it touches more than once, it's not a function. Now, we've been doing a lot of visual stuff with relations, looking at them, seeing its graph, reading the points. But no, this is algebra. What algebra stuff can I do with functions? Well, we have to talk about how do we write functions. Let's talk about the notation of functions. There's basically two notations you can use. There's equation notation, which, as the name implies, is just a regular equation. The only difference is you're going to have two variables, x's and y's. For example, y equals 3x plus 2 is an example of a linear equation which represents a function. But functions are so special, they get its own notation called, not surprisingly, function notation. All function notation is it takes away the outputs of y and it substitutes a name for a function. Names of functions are usually letters, say f for function, and at the same time it declares what the input value is. So for example, our example was y equals 3x plus 2. In function notation, it simply becomes f of x equals 3x plus 2. That's all function notation really is. Function notation has a label or a name. It has the input variable. And it has the rule or the equation. Right? Those are the parts or pieces of function notation. The reason why mathematicians use function notation is, again, I've already said it earlier, mathematicians, we're lazy. It's a very easy way to use a function. Remember the analogy I used was a vending machine. To use a vending machine, you have to press the button. Well, if I used equation notation, that's a lot of writing. But with function notations, it's very easy because all you have to do is change your input. For example, if I said this, hey guys, f of x equals, 4x minus 3 all over 2. Say, I'm just making this up. Then this notation, if you saw this, f parentheses 5, that is a set of instructions. That literally tells you plug in 5 for every x you see in the f function. Right. You can see why mathematicians use function notation. We can write out that sentence every single time, which is a pain in the butt, or we can just simply write f parentheses 5. So that's all function notation really is. It's a set of commands. Function notation just tells you to plug stuff in. What do we plug in? Whatever's inside those parentheses. So for this example, what would f of 5 be? F of 5 would be 4 parentheses 5 minus 3 all over 2. You do some math. 4 times 5 is 20, minus 3 is 17 over 2. We evaluated it. We found it. Okie dokie? Right. When you're just doing random equations, we call them inputs, outputs, x's and y's, but functions exist in everyday lives, right? We see a lot of input-output relations in the world that we live in. When we do talk about functions in the world we live in, we simply don't call them inputs and outputs because that's not fancy enough. We change our vocabulary a little bit. Yeah. So the idea is this. In real world situations, functions are sort of cause and effect relationships. Instead of having an input producing an output, we have an independent variable that's the vocab word, independent variable. And the independent variable is just playing the role as the input or the x values. The independent variable controls what happens to the dependent variable. And that's the other vocab word, dependent variable. And the dependent variable is playing the role as the output. Which are your y values. So it's the same thinking. You know, what am I putting in and what am I getting out? But instead of calling them input and outputs, we just call them independent and dependent variables. For example, let's say I go shopping, right? And I'm interested in how much money I'm going to spend. Well, you guys would agree that the amounts of items I buy will change how much money I spend, right? In that situation, the amount of items purchased is my independent variable, and my cost or my total bill would be the dependent variable, right? So that's just a little vocab thing. Don't get all tripped up. It's the same concept, inputs, outputs, but when we're talking about a real world situation, we just call them independent variables and dependent variables. Independent variables control what happens to the dependent variables. Any questions? That is the conclusion of 2.1.